So the second and last talk this afternoon is by Raghuram, and it's about special values of Rankin-Selberg L-functions over totally imaginary base field. Please start.
Okay, thank you very much. Can you hear me clearly? Hello?
Yes, we can.
Yeah, okay, very good. So thanks to the organizers for the invitation. I wish I were there. And I kind of wish I knew all the people, I could see all the people in the audience. I'm going to ask you to indulge me for a minute. ಯಾಕಂದ್ರೆ ನಾನು ಬೆಂಗಳೂರಿನಲ್ಲಿ ಲೆಕ್ಚರ್ ಇದ್ರೆ ಒಂಚೂರು ಕನ್ನಡ ಮಾತಾಡ್ಬಿಟ್ಟು ಕನ್ನಡ ಲೆಕ್ಚರ್ ಕೊಡೋಣ ಅನ್ಕೊಂಡೆ. ಆದ್ರೆ ನಾನು ಒಂಥರ ಬೆಂಗಳೂರಿನ ಮಣ್ಣಿನ ಮಗ ಸ್ಪೀಕ್. ಆದ್ರೆ ಕನ್ನಡ ಲೆಕ್ಚರ್ ಕೊಡೋಕ್ಕೆ ನಂಗೆ ಅಷ್ಟು ಕನ್ನಡ ಗೊತ್ತಿಲ್ಲ. ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಹೆಂಗೆ ಮಾತಾಡಬೇಕು ಅದಕ್ಕೆ ನಾನು ಇಂಗ್ಲಿಷ್ನಲ್ಲಿ. ಸೊ ಇಫ್ ಯು ಡೋಂಟ್ ಮೈಂಡ್ ಐ ವಿಲ್ ಗೆಟ್ ಬ್ಯಾಕ್ ಟು ಇಂಗ್ಲಿಷ್. ವಾಟ್ ಐ ವಾಸ್ ಜಸ್ಟ್ ಸೇಯಿಂಗ್ ವಾಸ್, I grew up in Bangalore and I speak Kannada, and it seems like I should give a talk in Kannada, but on the other hand, I think about mathematics in English. So if you don't mind, I'll just give a talk in English. Okay. So I want to speak about some recent work of mine on the special values of Rankin-Selberg L-functions over a totally imaginary base field. So to set the stage, I'm going to recall a classical example of Hurwitz. This goes back to 1897. It states that if you take the sum over all integers m and n, not both zero, of m plus in to the power 4k, then this is omega to the 4k up to a non-zero rational number. In fact, Hurwitz made that rational number also precise. And of course, you see the relation with Euler's classic formula, where zeta 2k would be pi to the 2k times the rational. And here omega is this period, the integral from -1 to 1 of dx by square root 1 minus x to the 4. This is a very beautiful formula, and this kind of is probably the most elementary non-trivial example that I can think of to motivate the sort of result I'm going to be talking about. So Hurwitz's formula can be recast as, if I take the field qi join the square root of -1, and I take this unramified Hecke character of this field f, defined as its value on an integral ideal A is a plus ib to the power 4. Oh, could someone let me know if you can see my cursor moving on the screen? Right now it's on a plus ib to the 4.
Yes, we can see it.
Okay, thank you.
So a thicker one would be better.
Thicker one would be better, and I have to figure out how to make a thicker one. Okay, I won't worry about it now. Okay, so it would have been better, but if anyone knows the quickest hack to make this cursor thicker, okay, never mind. So I take this unramified Hecke character defined as raising a generator of this integral of an ideal to the 4th power. Then raising to the 4th power, of course, the units are plus minus 1 and plus minus I, and this is well defined. And Hurwitz's formula above can be stated as the value of the Hecke L function attached to chi to the k at the point 4k is up to a non-zero rational number omega to the 4k. Okay. So one can deduce the following somewhat easy corollary to this result of Hurwitz. Let me just take k equals 1, the simplest situation. And I look at the L function of Ls chi, L function attached to chi. Then I look at these 4 points, the values at 1, 2, 3, and 4. As a corollary of the main theorem of this talk, it will follow that these L values differ from each other by something in qi. And of course, since the L4 is omega to the 4 times the rational, that could have been a rational, we know that all these L values are omega to the 4 times possibly something in qi. The main theorem in this particular example will take this shape, that the critical set, I'm going to tell you what a critical set is later on, but the critical set for this L function is this string of integers 1, 2, 3, and 4. And if I have any two successive points in this small set, then the ratio of these L values is in Qi. Okay. And the goal for this talk is to generalize a theorem of this kind to Rankin-Selberg L-functions for a product of general linear groups over a totally imaginary base field. I see something has popped up in chat. Okay, this is the. While giving my talk, I may not quite pay attention to the chat box, but please feel free to interrupt me anytime during the talk. I much rather prefer mathematical banter as against monologue. So now to state the theorem, I actually had to debate a little. I can do justice to developing the notations and the relevant theory to state the theorem, or do justice to the proof. So I decided I'll rather spend time picking up the preliminaries to state the theorem as precisely as I can. So here are some preliminaries headed towards that goal. So I want to introduce locally symmetric spaces. If I take F is going to be my totally imaginary field that's going to be fixed once and for all. G is going to be the restriction of scalars from F to Q of GLN over F. T, the restriction of scalars from F to Q of Tn, where Tn is this diagonal torus inside GLN. I'm going to take Z, the restriction of scalars of Zn, the center of GLN, the scalar matrices. And S is a sort of diagonal copy of GM inside this center. There's a maximal central split torus of the algebraic group G over Q. Sigma F is going to be the set of all embeddings, field embeddings of F to C. And there is a surjection from that to the set of S infinity, the set of real places. So V is going to be, if V is an Archimedean place, then there is a pair of complex conjugate embeddings, and you fix one of them. I'm just going to call that eta V. It's non-canonical choice, but that's kind of fixed for the whole game. And the other one is eta bar. If I look at the real points of this group G, then this is GLN of F tensor R. And then with this identification of F sub V, the completion of F at V being complex numbers via eta V, this is the product of GL and Cs. C infinity is going to be a maximal compact subgroup of GR, and this is just the product of unitary groups. And S, remember this maximal central split torus is, I'm going to look at the real points of that. S is just GM, so there's just R cross. And I'm going to let K infinity be the maximal compact subgroup thickened by a little bit of the center. There is a lot of choice in what I could take as possibly K infinity. I could have worked with C infinity. But that won't work because some space then won't have finite volume. I need to thicken it a little. So this is the bare minimum I can thicken it by in some sense. And we'll just note that K infinity is connected, as against, say, if you're working with elliptic modular forms or Hilbert modular forms or something, that the disconnectedness, you got to keep track of that. Anyway, so this K infinity is connected. I take Kf to be an open compact subgroup of GAF, where A is the ideals of Q and A sub F is the finite ideals. And my locally symmetric space, an idealic version of this is, I'm going to denote by SG sub Kf. It's GA mod GQ mod K infinity Kf. For example, this could be, if I take G is GL2 or say Qi, then, this is like the hyperbolic three space modulo Zi kind of space. Well, technically, this may not quite qualify as a locally symmetric space. I might have to take this open compact subgroup and shrink it a little so that there's no pinching to make some map being a covering map. But this is the space I'm going to work with. I can always pass to a subgroup of finite index and Kf if necessary. I want to introduce some sheaves on these locally symmetric spaces, for which I take a weight lambda is a weight on on T cross E. I have to tell you what is E. So F is my totally imaginary field, which is fixed once and for all. E is a finite at the moment Galois extension of Q, which takes a copy of F. This is going to be my field of coefficients. And later, as and when necessary, E could be, I can base change E, have to keep track of how all the objects behave under changing my E. I could even map to complex numbers if I will, I don't have to have E over Q to be finite, but it's basically a large enough extension which splits my group G. If I want to do periodic interpolation or anticipating that, you could take E to be some suitably finite large extension of QP. Anyway, so right now it's just a finite Galois extension of Q. So what does such a weight entail? So this weight is really is a tuple of weights lambda tau, where tau runs over embeddings of F to E, and each lambda tau is a string of integers lambda tau 1, lambda tau 2 through lambda tau n. Asking for this weight lambda to be a dominant integral weight is basically asking for these integers to be integers. I beg your pardon, these lambda tau j's to be integers. And dominance, okay, I have to fix a choice of a Borel. If I work with upper triangulars, then the dominance condition would be lambda tau 1 is bigger than or equal to dot, 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 bigger than or equal to lambda tau 1. It's a non-increasing sequence. I'm going to take m lambda e to be an algebraic, absolutely irreducible, finite dimensional representation of the algebraic group G cross E with highest weight lambda. And this representation gives me, by a standard construction, a sheaf of, since this over E is a sheaf of E vector spaces on my locally symmetric space SG sub KF. And now, one of the basic objects of interest is the cohomology of this space, this locally symmetric space with coefficients in this sheaf M lambda E. Now you got to remember, there's not just an E vector space, but there is an action of a Hecke algebra. All these cohomology groups are going to be Hecke modules. The Hecke algebra at site here is, I work with smooth, that's locally constant, compactly supported by KF invariant functions. I can take Q valued, you have to worry about choice of measure. Under a convolution algebra, there's an, under convolution, it's an algebra, it acts on these cohomology groups. I can also work with cohomology with compact supports, which I'll qualify with a little sub C there. And inner or interior cohomology is, by definition, the image of cohomology with compact supports inside global cohomology. I'm going to use the phrase inner. Interior is also used in the literature. This is inner cohomology, basic fact. It is semi-simple as a Hecke module. And right now, I'm working purely in an algebraic world of, everything is happening. The field of coefficient is this field E. But to see semi-simplicity, one makes this, you base change to complex numbers, and then you can appeal to the theory of automorphic forms. And basically, inner cohomology gets captured by some kind of cohomology of the global discrete spectrum of that group. So this is a good place to talk about how do I base change. So again, so far we had F over Q is a totally imaginary field, which is fixed once and for all. I take this field E, you should think of E as a floating field, it's Galois, and takes a copy of F. It's going to split my group G. And then I'm going to change E, and right now I want to change E all the way to complex numbers via an embedding I call iota. Now this embedding of fields, iota, induces a bijection of the field embeddings from F to E to the embeddings of F to C, which was denoted sigma F before. By just composition, I take a tau here and I map it to iota circle tau. This also induces a bijection from the group of characters of T cross E to the group of characters of T over complex numbers. If a lambda is written as a lambda tau running over embeddings of F to E, then iota will take this iota lambda, which is, there is one element iota lambda eta for every complex embedding eta of F to C. And then if I want to relate this to what parameterized lambda, then you have the recipe is iota lambda, the eta component is the eta inverse circle iota component of lambda. Something very natural, you don't have to worry about this little. And also I can base change my representation, m lambda e via iota to complex numbers, and then this would be the algebraic finite dimensional irreducible representation of the group G cross C with highest weight iota lambda. So I was talking about the Sheaf cohomology group, and now as an E-vector space, I base change that to complex numbers. This then is the Sheaf cohomology of this locally symmetric space with coefficients in m tilde iota lambda. Maybe there's a little bit of text which is getting cut off in my, slightly reduce it. Yeah. So there's a basic isomorphism here that this Sheaf cohomology group can be, if you think in terms of differential forms, and then you'll see that this Sheaf cohomology is isomorphic to what's called relatively algebra cohomology with coefficients in the space of smooth automorphic forms. This is the C infinity GM or GQ. And since I have some level structure KF, I have to take KF invariant functions of this space of smooth automorphic forms twisted by this finite dimensional coefficient system. And we keep in mind important theorem of Borel that the space of smooth cusp forms sitting inside the space of smooth automorphic forms induces an injection in cohomology. And therefore, on the Sheaf cohomology side, there is some subspace here, which we'll call cuspidal cohomology, that is mapped isomorphically to that part of the relatively algebra cohomology captured by the space of cusp forms. So this is the definition of cuspidal cohomology. We will call this group cuspidal cohomology of G with coefficients in m iota lambda C. This makes sense only after base change to complex numbers. So I want to talk about a certain issue involving this cuspidal cohomology. The point is not all weights lambda is going to support cuspidal cohomology. And there's a very important point for developing the story. So that's called purity. And I'll have to qualify that to something called strong purity. So let me just scroll up a little here. So first, what is purity? So there is a basic fact due to Clausel that if cuspidal cohomology is non-zero for some weight iota lambda, then this iota lambda needs to satisfy a purity condition. Okay. Now this weight iota lambda is parameterized by there's one component iota lambda eta for every complex embedding eta, and purity is some condition of this kind that the jth component of iota lambda and the n minus j plus 1th component of iota and eta bar complex conjugate, these have to add up to a constant. So what's happening? Let's just pause for a second. This j and n minus j plus 1, that's like taking a weight and hitting it by this while group element of longest length. Okay, so I'm working with the, so to speak, like the dual weight. And there's an eta and an eta bar. So this is a kind of polarization condition on the coefficient system that it's essentially, I say essentially because of it's got to add up to the W, it's essentially conjugate dual. Okay, the components, the eta and eta bar gets, they have to add up to this constant after one of them is hit by this while group element. So that's purity. It's a certain polarization condition that a weight has to satisfy for that weight to support cusp forms, okay, with cohomology with respect to that weight. Furthermore, another theorem of Clausel, both these theorems are there in his article in the Ann Arbor volumes, that cuspidal cohomology admits a rational structure. So this is the GLN statement of, if you go back to the world of elliptic modular forms and you work, say, modular forms of cusp forms of weight K and gamma naught n or gamma 1n, admits a basis with Q Fourier, with Fourier coefficients in Q rationals. So this is the general version of that. It admits a rational structure. In particular, it is stable under Galois conjugation. In particular, if a weight has to support cuspidal cohomology, then not only should this weight iota lambda be pure, but every Galois conjugate of iota lambda is got to be pure. And so this additional condition that every Galois conjugate is also pure, I will call that strong purity. So strong purity now takes this shape that, and I can talk about this for weights defined purely at an algebraic level. So I take a weight, I should have said a dominant integral weight for the torus for G cross E is strongly pure if, okay, this is a kind of handful of notation here, the j and the n minus j plus 1, that is one weight, and the other weight, sort of the dual weight, the eta and eta bar, one embedding and the conjugate embedding, and the iota and the gamma vary or all possible elements. Okay. So not only should iota one, for one embedding iota, should iota lambda be pure, but for every embedding iota, iota lambda should be pure. And this for every embedding iota, I'm going to call it strongly pure. And this was a point I hadn't appreciated very well until a few years ago. So let me kind of talk a little more about this condition of strong purity on the weight for it to support cuspidal cohomology or a totally imaginary field has some pretty serious consequences. So this is a good point to talk a little about the inner structure of a totally imaginary field. Here is my F is fixed once and for all, a totally imaginary field. I'm going to take F naught to be, let me just scroll down. Yeah. I'll take F naught to be a maximal totally real subfield. Compositum of two totally reals is totally real, so there's a maximal totally real subfield. It's an easy exercise then to see that there is at most one totally imaginary quadratic extension of this totally real F naught, maximal totally real F naught, contained inside F. Okay, it's an easy exercise. So this then gives you two cases. One case is where there is, in fact, there is such a unique totally imaginary quadratic extension of this maximal totally real subfield. In other words, this field F contains a CM field, and in which case I call F1 to be this maximal CM subfield of F. It's a totally imaginary quadratic extension of this maximal totally real F naught. I'm going to call that CM case. I'm not too happy with this terminology that I cooked up, but if someone has a better thing to suggest, I'm happy to go along. And the TR case is when F does not contain such a CM subfield. In other words, there's only a maximal totally real subfield. And these cases, both, one can cook up examples for both cases. And strong purity has this consequence that if I work with a weight which is strongly pure over a totally imaginary field, then there is in fact a strongly pure weight over this field F1. Okay. So that my original weight is in fact some kind of a base change of this weight over F1. I could say my weight descends to a weight over this field F1, which is kind of canonically cut out by this totally imaginary F. Base change in the sense that there is this lambda 1, so that the tau component, tau is, remember, was my symbol for an embedding from F to E. The tau component of lambda is the tau restricted to F1 component of lambda 1. Okay. So just a quick recap of my weights, what I've been talking about. I could work with the set of all possible weights, algebraic weights. That's too big. I need to work, this has to be giving me a coefficient system. So I'm going to work with dominant integral weights for the torus T, base change to a splitting field E. Inside this lives a subclass of pure weights. And inside that lives a subclass of strongly pure weights. In general, they're all strict inclusions. Here, purity meaning for some embedding, it's pure, and strong purity is for every embedding from E to C, the weight is pure. It's an exercise that if F is totally real or a CM field, then pure and strongly pure are the same. But in general, the class of strongly pure weights is smaller than the class of pure weights. Okay. And this causes some trouble for us later on, as we will see. Or it just trouble, or it caused me trouble in fixing proofs. Maybe a better way to say is it adds a certain layer of, an additional layer of detail, richness of details to the theorem that is going to follow. So now if I take such a strongly pure weight and I look for, I want to understand cuspidal cohomology that it can possibly support. And I want to qualify this theorem of Clauzel that there is a rational structure. In fact, that rational structure is visible at an algebraic level. The statement would be there is a Hecke subspace. I'm going to denote H dot shriek. strongly inner cohomology is what we call it. Inside the space of inner cohomology, this is all happening over E, totally algebraically, so that for any embedding from E to C, this strongly inner cohomology base changes to cuspidal cohomology. Okay. I'm going to call an isomorphism. Remember, there's a Hecke action on everything inside. An isomorphism class of an absolutely irreducible Hecke module appearing in strongly inner cohomology. I'll just call that such isomorphism classes as the strongly inner spectrum of G over F, GLN over F with coefficients in lambda over E. And since this strongly inner base changes to cuspidal cohomology, if I take the base change of sigma F to complex numbers, this in fact is the finite part of a cuspidal automorphic representation. I'm going to denote that iota sigma of GA, which is the same as GLN AF. Well, technically, since I have a level structure here, this iota sigma, I should say, is the KF invariance of the finite part of a cuspidal automorphic representation. Okay, that level structure is, you have to just carry through that baggage, but it's not, we can ignore it for most of this kind of a talk. And so to a pair of cuspidal automorphic representations, but for me, I'm going to work with those which have such an algebraic origin. So sigma F appears in the strongly inner spectrum of GLN over F with coefficients in mu over E. And this notation is to say already that mu needs to be a strongly per weight of the corresponding torus, all this over E. Likewise, if I take sigma prime, something in the strongly inner spectrum of GLN prime with its weight mu prime being strongly inner for the torus T sub n prime, n and n prime, of course, are just two positive integers. I take an embedding iota from E to C, then I got the a pair of cuspidal automorphic representations, iota sigma and iota sigma prime. And to this pair, I can consider the Rankin-Selberg L function, which is of degree n times n prime over F. I look at this Rankin-Selberg L function, and the goal is to understand the critical values of such an L function for a pair of GLs over this totally imaginary field. So this was, I know, a somewhat longish passage just to build my notations. Maybe I'll just pause for a second. If anyone has any questions, please ask me. Or maybe I should. I don't see anything in chat.
Can I ask you a question?
Yes, please.
This shriek is the same as cuspidal cohomology? Double shriek?
Not quite. Shriek is base changes to cuspidal cohomology. So shriek.
Rational structure.
It's a rational structure.
So the rational structure coming from this sort of Aikura-Shimura kind of things, actually this split. That's what this says. Yeah, one has to be a little, yes. That means Eisenstein part has the rational structure, then it would follow. Is that right? No, I'm not even touching the Eisenstein part at this moment. Yeah, I agree. But for entire thing, this rational structure coming from this type of Aikura-Shimura type things actually gives a rational structure. So if you can split this rational structure into cuspidal part and the Eisenstein part, then it would tell the shriek existence. Yeah, I'm only semi with you, but I guess that's right. Okay, thank you. I guess the point to appreciate here is this lives inside shriek, which is inner cohomology, and this inner cohomology is purely sheaf theoretically defined. And in my book with Harder over a totally real field, we carried through a certain kind of thinking through which this can be characterized totally intrinsically working with vector spaces over E and
just looking at the degrees, possible degrees in which there's contribution to cohomology, without even base changing to complex numbers. So in other words, for a totally real field, one reproves Clausel. Oh, this totally imaginary, I actually just, I sidestepped that issue and I just used Clausel to say that there exists this kind of a shriek thing based on Clausel's theorem that this is Galois stable, cuspidal cohomology is Galois stable.
Okay, thank you.
Any other questions? Okay, if not, let me move on. So now I want to get into what is the main result that I have about these kind of the critical values of Rankin-Selberg L-functions for a pair of general linear groups or a totally imaginary field. So here is the main theorem. It will take me a couple of pages to little more. I got to introduce something more. So once again, my notations are sigma f is in the strongly inner spectrum of GLN over F with coefficients in mu over E. With an embedding iota, this will base change to the finite part of a cuspidal automorphic representation of GLN over AF. And this weight mu is to be a strongly pure weight. So it has its purity, the mu and that mu, the mu eta and the mu eta bar after that while group element add up to some constant, and that's that constant W. It's called the purity weight of that highest weight mu. Likewise, sigma sub sigma prime F for GLN prime, analogous notations. Capital N is going to be the sum of these two integers, n and n prime. Definition: a half integer m, a possibly half integer, which lives in capital N by 2, depends on the parity of capital N, is critical for this Rankin-Selberg L function. By definition, it's critical if the gamma factors on either side of the functional equation. Oh, I'm missing a dual here, sorry. So the gamma factors on either side of the functional equation should be finite. Okay, no poles. They got to be regular at this s equals m. So this is on one side, and on the other side, the value at 1 minus s of iota sigma dual, and this should be iota sigma prime. There should be a little check there, dualized. These got to be finite at s equals m. I need to introduce some combinatorial information deduced from the weights mu and mu prime. I'm going to call the abelian width between mu and mu prime to be the quantity. I'm going to denote it A, mu comma mu prime, which is W minus W prime by 2, the difference in the purity weights in some sense. There's a different way to package information about the weights using, say, fundamental weights and the determinant character, and then there's an abelian part of weight mu and a semisimple part. And some of this is, if I packaged information about mu and mu prime in that notation, then the adjective abelian is kind of clear. And then you work with the rest of it, the semisimple part, and this contributes to what I call the cuspidal parameters. So let me simply say for every Archimedean place V, one introduces a string of numbers, alpha V1, alpha V2 through alpha Vn, and similarly beta V1, beta V2 to beta V. And what are these alpha and beta, alpha V and beta V? These are, these give you the inducing data somehow for the representation at infinity. The rho sub n is half the sum of positive roots for GLN. You can just completely ignore that here. And if you're familiar with these things, what is happening and on the back, sort of behind the curtain, is there is a Wigner's lemma at play. And one can, if I know a cuspidal automorphic representation as cohomology with respect to some highest weight, then the representation at infinity is essentially pinned down by that highest weight, using Wigner's lemma and using the fact that for GLN, everything is globally generic, so locally generic. You have to put some thoughts together, and you can deduce that the component at V of this cuspidal representation, iota sigma, is a simple-minded, beautiful, fully induced representation induced from the Borel of Bn, the Borel of GLN to GLNC of characters that I put on the torus. And the exponents, I just basically identify the exponents, and they are called the cuspidal parameters. These cuspidal parameters, you have to see how far apart they are, and then some minimum of absolute value of some blah, 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 running over all Archimedean places, running over all possible indices I and J. Roughly speaking, the exponents of the inducing data for sigma and the exponents for the inducing data for sigma prime, you want to see how far apart they are, the least possible distance between them. That I'm going to call as the cuspidal width between mu and mu prime. And the proposition is that the critical set, the set of points, there's half integers where the gamma factors on either side of the functional equations are finite, is the string of points between 1 minus L by 2 plus A and L by 2 plus A. L being this L mu comma mu prime and A being A mu comma mu prime. If you just stare at these inequalities, that abelian width is just shifting the whole game. Okay, so I might as well just ignore it. These are all the possible half integers between 1 minus L by 2 and L by 2. And do a simple calculation, you'll see that how many critical points do I have? The cardinality of the critical set is as many as the cuspidal width between mu and mu prime. Already there is a kind of notational simplification. There was an iota in my data to which I'm attaching the L function, but in the critical set, I've suppressed the iota because it's an exercise that the cuspidal width is independent of the embedding iota. So that's, one can totally and completely identify the critical set. If I go back to the Riemann zeta function, of course, that's over Q, but nevertheless, if I go back to the Riemann zeta function, the critical set for the Riemann zeta function are the even positive integers, 2, 4, 6, etc., and the odd negative integers. The critical set is always symmetric with respect to the functional equation by definition. Okay, so the definition is symmetric with respect to the functional equation. And but over a totally imaginary field, it's a finite set. Okay. Somewhat like what happens for a modular form of weight k, the critical set for the L function would be 1, 2, 3 up to k minus 1. Okay, having identified the critical set, now I can state the theorem. So I start with, say, notation sigma f and sigma prime f, strongly inner spectrum, living strongly in a spectrum of GLN and GLN prime with weights mu and mu prime, strongly pure weights mu and mu prime. I'm going to assume for my theorem that the cuspidal width between mu and mu prime is at least 2. Okay, I need just enough space to guarantee myself that there are at least 2 critical points. The nature of this theorem is about ratio of critical values, so I need at least 2 critical points. Okay, so that's my assumption. First statement, since I'm going to be talking about ratio of L values, I want to say something about the possible denominator. If a critical value is 0 for some iota, then it vanishes for every iota. Okay. Now, if you look at Deligne's article in Corvallis, the one on period integrals, you'll see that there's a conjecture of Gross, which states that the order of vanishing, it's more than just vanishing, the order of vanishing is in some sense independent of what Galois conjugate of that motive I'm going to look at. So it's in that sense. So if one vanishes, then every conjugate vanishes. Okay. So I might as well, I'm going to assume, I should have stuck that in here somewhere, that the value at m plus 1 of this Rankin-Selberg L function is not 0. Then, if I were to be in that case where f contains a CM subfield, then the theorem is the ratio of, I forgot to say this, completed L functions. My notation LS blah is always stands for the completed L function. Okay, I'm including the gamma factors at infinity. So the ratio of completed L functions at 2 successive critical points for the Rankin-Selberg situation, I'll be dualizing the second representation, but that's just a technical point. You can just ignore that check. Times the discriminant. Delta sub f over q is the absolute discriminant of f over q. I take the absolute value and raise it to n prime by 2. Sigma lives on GLN, sigma prime on GLN prime. Okay, that's n and n prime. So the discriminant to the power n prime by 2 times the ratio of L values is algebraic. Well, not only algebraic, it lives in this field of coefficients iota e. Furthermore, since it's an iota e, I can hit it by any element in Galois q bar over q. So if I hit this quantity by an element gamma and the Galois group of q bar over q, then gamma on this quantity is this quantity for the gamma conjugated objects, except up to a signature, and this signature drove me absolutely crazy for the last 2 years. I'm just going to call this epsilon and epsilon tilde. There are two signatures, one coming from a representation and another somehow coming from the dual side. I will, at this moment, I'm just saying there are some signatures. So this quantity, this which lives in the rationality field, is Galois equivariant up to a signature. So it's some kind of a reciprocity law. The signature can be made very precise. It's just very complicated in this kind of a talk to make it precise, but there is some signature. However, if F does not contain a CM subfield, in other words, there's only a totally real subfield, there's no totally imaginary quadratic or that totally real, then necessarily this n times n prime is even. So this excludes, for example, the situation of just the L function of a Hecke character. Then since n prime is even, this discriminant term, this is just a rational number. So I just throw it under the carpet. This ratio of critical values for the completed L function, or the Rankin-Selberg L function, is rational and is Galois equivariant. So it's a kind of cleaner looking statement for the totally imaginary fields without a CM subfield. So these signatures are, like I already mentioned, are somewhat complicated. I will later, when I give you some hints about the proof, I hope to remember just to tell you how it shows up. And it's a fact that the product of these two signatures is in fact one. So let me go back to this situation where this is presumably the more interesting situation, where there is a CM subfield. Some people prove theorems just over a CM field. There, the individual epsilon and the epsilon tilde can be non-trivial. However, the product becomes trivial. So if F is actually a CM field, then the theorem is discriminant to this power times the ratio of L values is algebraic and Galois equivariant. Okay. So that's this comment here. The product of these two signatures is trivial, is F itself is a CM subfield. F itself is a CM field and can be non-trivial in general. Not only the individual epsilon and epsilon tilde, but the product can be non-trivial in general. So let me just briefly mention some literature. I just put some in quotes because this is not a historical, I'm not talking about the entire history of all theorems about special values, a totally imaginary field, but some theorems relevant to this paper, and certainly the papers I had to look at to kind of get myself going. There's a paper of Mogla. I have to tell you this, sorry for scrolling, but this statement that it's important to mention this, if a critical value vanishes for one iota for Rankin-Selberg, then it vanishes for every iota. This is a result due to Mogla in this long paper in Kröller about 20 years ago. Similar objects and constructions, but the proof actually is different. If I were to work with n and n prime both being one, that's like working with Hecke L functions. Then there's, of course, Blais's thesis and his paper where he proves Deligne's conjecture for, I think, the base field or CM field there. And Harder, his inventionist paper, which I will talk a little more about later. And then there is Hida's long paper in Duke, which is the definitive statement for GL2 cross GL2 and GL2 cross GL1. I have to say that, these Blaisius and Hida, these are statements about individual critical values. And therefore, you can deduce something about ratio of critical values. These are stronger. They're telling you about all critical values. There is this long paper of Harris and Kröller about periods of polarized motives, which is a statement about L functions for unitary groups in GLN cross GLN minus 1. So when n prime is just 1 off n, then I have some work, and there's a paper of Grobner and Harris and Fabian Januszewski, in different contexts for critical values of those L functions, and therefore you can deduce something for ratio of L values. There was a student of Harris, Grenier, who there was a somewhat slightly weaker theorem for GLN cross GLN. My student Gunja Sachdeva worked on GL3 cross GL1, and then there's been this long series of papers of Grobner with Sachdeva. G. Lin was Harris's student. Then Grosvenor Lin, Grosvenor Harris Lin. So this is like one long cluster of long papers, where ultimately in Grosvenor Harris Lin they prove a version of Deligne's conjecture for or a CM field. And I am building in this paper on my work with Hida, which was all about GLN cross GLN prime over a totally real field. Okay, so this is just a brief glimpse into the literature of what has been done. It's by no means exhaustive. So already people will know that I have not even mentioned Damerel and Shimura for CM fields there. It's, there's a huge, anyway. So just a few words about the proof, and then I want to give you a one sort of page summary of the proof. So first of all, the techniques of the proof generalizes Hida's inventionist paper on Eisenstein cohomology for GL2. And then later my book with Hida for Rankin-Selberg for totally real fields. The idea is to somehow exploit aspects of rank 1 Eisenstein cohomology for another general linear group, sort of bigger general linear group, GL capital N, where capital N is n plus n prime. And in the process of understanding what that Eisenstein cohomology is, you got to bring in the Burrell-Serre compactification. So my original locally symmetric space for the group GLN, it's not compact. You compact, there are several compactifications. The Burrell-Serre, they attach a boundary, the Burrell-Serre boundary. There's one piece of the boundary for every GQ conjugacy class of parabolic subgroups P. Okay. So these are just some words to tell you what kind of ingredients go into the proof. Now here is I'd like to give you a one page. Let me see, maybe just this, keep just this much. So G is GL capital N. I fix a parabolic P, a maximal parabolic, whose Levy is GLN cross GLN prime. And Q is going to be the associate parabolic. So all my parabolics I'm going to conjugate so that they all contain a fixed Borel. And then in this case, the associate parabolic is that of type whose Levy is GLN prime cross GLN. It flips. Okay. The game starts here. I start with sigma and sigma prime, and I work with this algebraically induced representation from the parabolic P, the group G of sigma cross sigma prime, algebraic induction, no, by which I mean it's not normalized parabolic induction. And the first technical step is to somehow realize this as contributing to the cohomology of that part of the boundary, del P, okay, del P is GLN, that part of the Burrell-Serre boundary in a special degree B sub n. So this involves some Weil group combinatorics, which was some amount of work for me. The statement is there is a representative, there is a constant representative for that parabolic, which what it does is it takes the weights mu and mu prime on GLN and GLN prime. You just stack them together to get a weight, no longer dominant, not in general, on GL capital N. You kind of straighten it out using a Weil group element of a special type, a constant representative for that parabolic, and make it dominant. Not only that, I wanted to make it dominant to be just so, in the sense that the length of this Weil group element should be half the dimension of the unipotent radical. We call this as balanced constant representatives. In which case, then the degree in which I look at cohomology is going to be B sub little n is the smallest degree in which cuspidal cohomology survives for GLN. Likewise for GLN prime, and then half the dimension of the unipotent radical. So this combinatorial lemma has a lot of important consequences that kind of permeate through the proof. In any case, that's where you start. You arrange for an induced representation to appear in boundary cohomology. Okay, and I'll call such a module as I sub P. Now we'll have to keep a certain standard intertwining operator between this induced representation and its partner, which is essentially the same inducing data, but now on the associate parabolic. I'm going to call that I sub Q. And now we get to the second part of this, the second technical result. So if I look at the total cohomology, well, there's a restriction map from that to the cohomology of the boundary. And there is this statement to prove, which we call the Main-Dsinfeld Principle, that the sum of these two induced modules splits off as a Hecker summand inside this boundary cohomology. In other words, these two are, there's an intertwining operator between the two. They're the same set of eigenvalues. That system of eigenvalues does not appear anywhere else in boundary cohomology. This uses classification results of Jacquet and Shalaika. So this IP direct sum IQ splits off as an isotypical summand from all of boundary cohomology. Okay. And in some sense, in parallel, one is also putting details about the standard intertwining operator between this induced representation and its partner. So one needs to keep in mind the famous calculation of Langlands that at an unramified finite place, the standard intertwining operator takes a normalized spherical vector, that is my F-free circle, to a spherical vector on the other side. And so it differs from the normalized spherical vector on the other side by some scalar. And Langlands apparently did this calculations in some summer, trying to figure out what the scalar is. And turns out there's a ratio of L values. Turns out it's the ratio at minus n by 2 and 1 minus n by 2. Okay. And there are other local subproblems to solve for Archimedean and ramified places, which in this kind of a talk I cannot get into. But there are some local challenges to be overcome. And then once one has all that in place, so back to this, from the global cohomology, you restrict to cohomology of the boundary, project onto this, the sum of these two pieces, and you ask for what is the image of this, and observe all these are just happening over E so far. And the image, the main theorem, you should pretend that each IP is like a line, and this IQ is another line. So this is like a plane, and the image of this global cohomology on this plane is like a line in this plane, okay? So the main technical theorem is to prove that the image of total cohomology in the sum of these two pieces looks like a class here and some partner of that class, which I call T sub I, is like an Eisenstein operator, so to speak, of applied to Xi. So this, how am I doing on time? I have 5 more minutes, right? I have 5 more minutes, right? I have 2 stopping points. I could stop here, or I could, can someone tell me? Have I put everyone to sleep?
You have even 8 minutes left, 7.
Okay. Okay, very good. So 7 minutes, all right. So I will go on for 5 minutes and then I will maybe some questions. So this is the essence of the proof, the summarizing what happened in this diagram, okay? The image of this inside this sum of IP and IQ, and one has to characterize that image. It's like a line in a plane. And so everything is happening. I have a 2-dimensional E vector space, and I got a 1-dimensional E subspace. I can look at the slope of that line, and the slope of that line is a number in E. That slope, if I put together Langlands' calculation, is, lo and behold, the ratio of L values. Okay, so that's how one proves this. And now there is, I have to tell you in 4 minutes now, that this result is compatible with Deligne's conjecture. So to talk about compatibility, so Deligne has this very famous conjecture about the critical values of motivic L-functions. It's one of his 2 articles in Corvallis. And amazingly, every theorem on critical values modulo the dictionary between motives and automorphic forms is compatible with Deligne's conjecture. So now that there is some theorem that one is looking at, question, is it compatible? So towards that compatibility, I go back to this configuration of fields. F0 is my totally real, maximal totally real, and F1 is this maybe totally imaginary quadratic, or it's just F0. Okay. So in the CM case, when F1 is indeed a CM field, I take an element D in this totally real field, which is totally negative, and I join square. Suppose F1 comes like that. I take the norm from F0 to Q of this quantity D and take its square root. I call that delta sub F1. So that's some number here, some kind of a discriminant term. And in the totally real case, I just define delta sub F1 to be 1. And delta sub F, up here is just raise it to this degree, f over f1, okay? And here's a proposition which is there in this ongoing work with Deligne about understanding ratios of his periods attached to motives. So, of course, I didn't in this talk develop, my notations for motives. So this is for those who are familiar with Deligne's notations. It goes like this. So if I take a pure motive over F with coefficients in E of some rank R, and I want to work with a motive over Q, so I just restrict from F to Q. And I want to work with critical points. I'm going to assume that this M, this restriction of scalars, has no middle Hodge type. Then the result is that the ratio of Deligne's periods defined in this Corvallis article is 1 tensor delta F to the power R, where you have to, his periods live in this E tensor C, and modulo this diagonal E star acting on E tensor C, it is 1 tensor, it's delta F to the R, basically. Think of it as just delta F to the R. And then the question becomes, well, is my theorem compatible with Deligne's conjecture? Then here comes a proposition which is an equality of signatures. I didn't tell you the epsilon and epsilon tilde. I'll just go back.
Here's what I found.
That the discriminant term which appears in as a multiplier in the ratio of L values for me, the gamma conjugate of the discriminant divided by that power of the discriminant is equal to this painful product of signatures times a gamma conjugate of a power of I times delta F to some power. Every term here, the left-hand side is plus minus 1. Each of the epsilon and epsilon tilde is plus minus 1. And this last quantity here is a plus minus 1. So one had to prove an equality of signatures. And this just drove me nuts all through the pandemic. This is proving this proposition has taken me more than a year, almost 2 years. And then after having done that, one has a cleaner statement that this ratio of L values for critical points at completed L functions times a power of I times that discriminant like term, delta F, to the power n times n prime, gln and gln prime, those n and n prime, is rational and is very beautifully Galois equivariant. And where is this gamma? So sorry for scrolling again. So let me just go back to this. To understand what happens under Galois conjugation, you have to go back to this configuration of objects and maps and hit everything by gamma. Okay. Or maybe first apply iota, write down the corresponding configuration of objects and maps after having base change by iota, and then hit it by gamma. And upon doing so, not all objects here are Galois equivariant, especially this boundary cohomology and some unipotent cohomology groups which will appear there. So upon hitting by gamma, sometimes there's some signatures which show up. So that's the epsilon and epsilon tilde. That's where they arise from. So let me just scroll back here and leave this as the main theorem. And then I thank you very much for your attention. I'm very happy to take questions.
Thank you very much. Yeah, are there questions in the audience?
So my question is back, and I don't know if it makes sense, but you're working over E vector space local system and rationality.
Yes.
And is it somehow possible to work everything integrally, like OE localized primes of P and some result of refinement? So P localized version of integral result.
Yeah. So, of course, in the progression of results on special values of L functions, once the analytic theory is in place and you prove something about special values like rationality results, the next step, which is a very hard step, is to ask for integrality results. I have not carried that in this article or in this talk. It is, it's very much there out in the distance. One has to ask these questions. So at this moment, I don't have anything to offer about P integrality aspects of a rationality result like this. But it's, yeah, I mean, as for people, anyone who's thought a little about this, torsion in integral cohomology is a major abstraction. In my answer to your question is that's a very interesting question. That is a natural question to ask, and I really have nothing to say about it at this moment.
Further questions or comments? So I can't see in the chat. There's no question, but here's another one by.
So, I mean, you use in the key step that you start from the maximal parabolic subgroup and you restrict it to the Borel-Sayre compactification boundary, and that you project down to the Hecke equivariant part of your. So then you have two. What is this letter? I don't know, AP or AQ or something like that.
It's a calligraphic I. Okay, IP. Okay.
IP and IQ. So the Eisenstein series has two I's. But if you start from non-maximal parabolic, then it can't be like that, right? And it has contribution from maximal things containing that parabolic, and it gives you a quite complicated thing. That's the main point, that you only did the Rankin-Selberg, I mean, tensor product of two. Is that right?
That's absolutely right. So if the parabolic is not maximal and I go a little deeper, say I work with GL2 cross GL2 cross GL2 sitting in GL6, so there's a spectral sequence which is built from the cohomology of this various strata which converges to the cohomology of the boundary. It's somehow sitting in a deeper part of the spectral sequence, when you're not in a maximal parabolic situation. So the adjective rank 1 Eisenstein, the rank 1 for the Eisenstein cohomology is to say that I'm working with this rank 1 parabolic, in other words, maximal parabolics. So deeper parabolics, I certainly haven't had, I don't have anything to say. It's much harder. Of course, Harder has thought some more about this, what happens when you're deeper inside that spectral sequence. So
do you hear me? Yes, Günther Harder, do you hear me? No. Yeah. Yeah, so I think this is a very, very interesting question. So if you, to go deeper into the spectral sequence, not only to look at the maximal parabolics or the parabolics in between, but this is very complicated and difficult problem. So some people are working on it. Do you hear me? No.
Do people in the audience, did they hear Günther Harder's answer?
Yes.
Yeah, okay.
So the spectral sequence is quite complicated, so you can't separate where like this. In the maximal parabolic case, there are two pieces, but for the non-maximal case, you have a lot of sort of, filtration. Yes. And that's why it's very hard to make a kind of correspondence like that.
But you may expect very interesting theorems. So I think, I do not know, but I think it may happen that multiple zeta values and something occur if you do this discussion. So I think it's worthwhile to try to go deeper into the spectral sequence and to go deeper into the cohomology of the boundary.
Of course.
I think you can dig out interesting theorems, but you have to work hard.
Yeah. That's difficult.
Yeah. Who is the speaking on the other side? Is it Hida?
Yes.
Hida. Yeah.
Okay. Yeah.
Thank you.
Okay. Is there any other question or comment? So then let's speak. Thanks the speaker again for this wonderful talk.
Thank you. let me ask a question to the local participants. So this is not mathematics, but ICTS trivia question. Have you seen the bust of Harishchandra in the library? It used to be in the library 3 years ago. Anyone seen this bust of Harishchandra?
Yes, I have.
Okay, very good. So there is an interesting history to this bust. You know, this bust was made by Charlotte Langlands, which you have no doubt heard this name. And there are just 3 copies of this bust. One in ISER Pune, where I used to work. One at the Institute for Advanced Study in Princeton. And the third one was made for ICTS. So the last time I was there, that bust had just arrived and I'd put it in the library. And I was wondering if it was there. And there was still some information missing about who made the bust. And there was a little write-up. I wish I were there. I really wanted to go see the bust and how they've displayed it and so on. And if those of you who haven't seen it, go to the library. As you enter, it's somewhere close to the entrance, that circular building in ICTS.
So
Okay.
you have some program before dinner then? If
Yeah.
I don't know. Yeah, so thanks a lot for your talk and goodbye. And also greetings to Günther Harder to Germany.
Yeah. Okay, thank you very much.